Hello everyone and welcome back to another video. Today I wanted to make another math video, and this will be the second part in a three-part series that I'm making as kind of an introduction to mathematical proof, which also can serve as an introduction into some higher level mathematical concepts and higher level mathematical fields. And I want to release these math videos at a monthly cadence. So it's going to kind of break up some of the philosophy Christian videos that some of you may have subscribed for. But for new subscribers, just know that I am planning to do these at a monthly cadence, so expect more Christian or philosophy content next week. But without further ado, let me just jump right into the video. So today we're going to be talking about sets. And I want to give a brief introduction to what sets are, and then some introduction to how we combine them and different operations with sets that can be performed. So as a brief introduction, in the most simple definition of sets that we can possibly give, a set is just a collection of things. So a set is a collection of things, or a collection of objects. And these things are called elements. So this is the most simple definition. This is there are certain restrictions that we have to make about the type of things that can go in to avoid paradoxes that we're going to get into later in this video. But to begin with, just to understand what a set is in its most simple form, it's a collection of things. And when we define sets, we typically put the things included in the set in these curly braces here. So an example of a set could be the numbers 2, 4, 6, and 8. That could be one set, just the first 4 even numbers. Let me write an example sign up here. Another example, it doesn't have to just be numbers. We can do words, like we could do the 4 seasons. So we could do spring, summer, fall, and winter. And we can also have sets that are a collection of sets as well. So we could have a set that is 1, 2, and 5. So it's just a collection of things in its most simple definition. And then some examples of important sets are some other examples of very important sets are the set of all integers. So this is the set of all integers. So for example, you have all integers, so all the numbers, including all the whole negative numbers, including 0, including all these numbers. It's a discrete set here. So this is the set of all integers. We also have an empty set, which is an important set. It's the set that has no elements in it. It has nothing in it. We also have the natural numbers, which I'm going to use this definition. It's all the positive whole numbers. And sometimes 0 is included, sometimes it's excluded. I prefer to exclude it in my definition. And then refer to the whole numbers as 0, as the natural numbers plus 0. But people have different preferences. So sometimes you'll see the natural numbers including the number 0. And also these ... just mean it continues on to infinity in both directions. And then the rational numbers. This is the set of all numbers that can be written as a fraction. as a fraction of two integers, so an integer in the numerator and the integer in the denominator. And then some examples of this might be like 1/2, 1/4, 3/11. And then famously, one example that's not in the set is the square root of 2. So those are the rational numbers. And then finally we have the real numbers. And these are all numbers that you can put on a number line stretching from -infinity to all the way to infinity. Let me fill in this one too. So any number that you could put on a number line. So you say you have 0, 1, 2, 3, 4. Like one example of this could be the number pi, which is 3.1415926535897, and continues on going forever. So this number you can't write as a fraction, but it is a real number because it fits on the real number line. Another one would be the square root of 2, like we talked about before, which is like 1.41. And then, yeah, so those are some examples of important sets in the field of mathematics, and in math we're going to refer to these all the time, talk about integer, especially I want to do a number theory series, and we're going to talk about the natural numbers constantly, or if you go into analysis you're going to talk about the real numbers constantly. Yeah, so after this, let's go into a little bit more. So with this basic framework of what sets are, let's jump into some notation that we use. So typically when we talk about sets and when we denote sets, we use capital letters. So for example, let's think about the first set that we looked at, A, and we'll call it A from before. 2, 4, 6, 8. So we typically use capital letters to refer to sets, and we use a epsilon, this symbol here, to denote that an object is an element of. And I'll use just this is like shorthand for element, and then this symbol to say is not an element of. And once again, this just means element. So, for example, we could use this to say for this set A, we could say 2 is an element of A, but on the other hand, 5 is not an element of A. So that's how you could use these two symbols here. And then for more notation, we have what is called set builder notation. Oh, I scrolled up accidentally. Still getting used to working in this pen. I bought one of these like nice Wacom pads and pens, which is super nice for making these videos. Oh wait, yeah, it's super nice for making these videos, but I'm still getting used to holding this pen and trying to write with it. So we have set builder notation. And this is typically how you'll see sets defined in math. So the way it works, you have your set, and that set is equal to some expression and then there's a colon here, and then some rule. So to understand this a little bit better, let's look at an example. So let's say we have this example where E is the set of all even numbers. So one way we can see this is, the first example we could look at this where E is the collection of elements n that are integers. So here's our expression. We have E is all the n's that are integers where this rule is true, and the rule is that simply that n is even. Now this is one way to write it. Another way, because there's not one unique way to write these things, another way is to say, and this is more actually mathematically helpful in proofs, just saying n is even isn't necessarily helpful in proofs. E is all two n's, or anything that can be constructed as 2n where n is in the set of integers. So it's all numbers that are divisible by 2, basically, or anything that is 2 that we can find some value of n that's an integer where the element is equal to 2n. So it's all these 2n's basically. Okay, so with all this notation out of the way, let's jump into some examples of things. Let's start with the concept of a subset here. Let me actually just divide things off quick so that we have things kind of separated. So that we can kind of follow along with what we've done so far and what we haven't done yet. Okay, so now let's go over here, or actually let's go up here. Let's look at the concept of a subset. So we're going to start with two sets, A and B. And we say that A is a subset of B. That's what this notation means. It means is a subset of. We say A is a subset of B if every element of A is also an element of B. Okay, so let's start there. So what does this mean? Let's think of, and then also we have the notation, this means is not a subset of. With this, let's think of an example. Let's look at an example where B equals A, B, C. It's just this set of letters. So here what we have is what is the list of all of the subsets of B. So one subset is the empty set. We just defined the empty set as a subset of all sets. That is just one mathematical fact. That's by custom. And next, another one is the set that only contains A, because every element of A is also an element of B. A is an element of B. So that's the one subset. Here's another subset. Here's another subset. So these are all of the subsets. And then finally, every set is a subset of itself. So this one is B. Every set is a subset of itself, because every element that it contains, it also contains. That's trivially true. Now, if we want to think about what this set is, this set of all the subsets is known as the power set of B. And the symbol for this is very weird. Let's see if I can actually draw this on my... Okay, that's not bad actually. So this is the set of all subsets is known as the power set of B. And I haven't used power sets very much in my mathematical proofs, but I think I'm sure there's some areas where they're important. But yeah, so that those subsets are known as the power set. So to further clarify what a subset is and how that's different from something being in something, let's consider these examples. Oh, and then also one thing that's the case, the number of elements or the number of subsets of a set is equal to 2 to the power of n. And one way to understand why this is because we have a choice to include or exclude every single element. So every single element here, if there's n elements, every single element, there's 2 choices, include, exclude. And then if you take each of those combinations, there are 2 to the n ways, 2 times 2 times 2 for all n elements. There's that many ways to include or exclude each of the elements. So that means you have 2 to the n subsets of a given set. So another example we have, let's look at some examples here. So let's look at this set. Actually, one second, let me give it a name. Let's call this set Y. So let's look at the number 1. 1 is an element of Y. However, 1 is not a subset of Y, because 1 in this case is not a set. It's not a set of objects. It is one of the objects. So in that sense, it's not a subset of Y. It's simply an element of Y. On the other hand, the number 1 is contained by Y because of this element. So you can see this set that only contains 1 is an element of Y. And the number 1, or this set that only contains 1, is also a subset of Y, because this element 1 is also contained here by Y. Now, if we wanted this to not be an element of Y, let's define a new set, Y prime. So if Y prime was just equal to this element 1, the set that just contains 1 would not be an element of Y prime, but it would still remain a subset of Y prime, because every element contained here is contained in Y prime. So I hope that makes sense. That explains kind of some of the differences between what it means to be an element of something, to be an element of a set, versus to be a subset of a set. And I know right when you kind of get into these concepts, it can be a little bit difficult to distinguish between some of this notation early on. Just so that I think this clarifies a little bit what some of these differences are. And with that, so let's close off our discussion on subsets now. And now we can move into how we can combine different sets. So let's look at different ways to combine sets. First, One common way to visualize visualize multiple different sets and what's contained in each is a Venn diagram. And a Venn diagram is, I'm sure you guys have all seen these before in school. It's named after a British logician, John Venn, and basically this tool visualizes sets as a circle for each set, and basically a circle for each set. So say we have sets A and B. A refers to all the elements contained in A, B refers to all the elements contained in set B, and this overlapping space here refers to elements contained by both. So let's work with some instances of things that combine two different sets. So first, let's look at the concept of a union. And in this context, it is A union B. And this is the symbol for union. That's this little U here. And what it basically means is X. It's all elements where X is in A or X is in B. And if you remember from our mathematical logic video, you can look into that to see more of what this OR means. And this is also symbolized as this V from OR from before, if you remember that first video. Now, the way this looks on a Venn diagram, you have set A and you have set B. And the union refers to everything that is contained by both of these sets. So it refers to this entire Venn diagram. Up next, let's look at the concept of an intersection. And this is denoted by this symbol, this upside down U. A and B. That's the intersection of A and B. And this is all elements where X is in A and X is in B. And once again here we have the same and that we talked about in the mathematical logic video. That's denoted by the little upside down V. And here, what this refers to with the elements of the sets, it's all elements that are contained by both A and B. So it's just this little strip in the middle here. And then finally, the last combination of sets that we're going to talk about here is the difference. And this is denoted using the minus sign, and that it's defined by X, where X is in A and X is not in B. Okay, so in this case, what we have here, we have this Venn diagram, and this Venn diagram of A and B so it refers to everything that's in A but not in B, so it doesn't include this little sliver here. Additionally, I didn't put this in my notes originally, but one other way to combine two different sets is a Cartesian product. And there's not a Venn diagram for this. This is another symbol that you might see. Oh wait, why did I do an IO? That's funny. So the Cartesian product is basically you create a new set, and that new set combines a bunch of ordered pairs for each element of A and B. So the way it works, you create a Cartesian product where it's all things that all A's and B's, where all the A is in A, so it's all combinations of the elements in A and the elements in B. So an example of this could be, let's say A is equal to A B, and B is equal to B C. A times B is equal to, oh wait, no, we're doing ordered pairs. So it'd be ordered pairs where A, B, A, C, B, 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 C. So that's a fourth way to combine two different sets, is the Cartesian product. So if you see this X symbol multiplying two sets together, basically, that is the Cartesian product. But then other than that, these are the most common ways that you see to combine two different sets, and they're represented by those Venn diagrams. Now, actually, before moving on here, let's look at a few examples of, or at one example of these different operations that you can do. So say A, let me scoot over a little bit too. We'll say A is this set, and B is this set. So if we wanted to make a Venn diagram of this first, because this might help us understand later on what we need. So notice that A has A, B, C in it, and then both have D and E, and then only B has F. So this would be how you draw out a Venn diagram of this. And the way to think about these different combination sets is you have A union B, and this has all 6 of these elements: A, B, C, D, E, F. Because if you recall from before, it includes everything that's in A or B. Next, we have the intersection of A and B. And this only contains D and E, because the intersection creates a new set that has elements that are contained by both of the sets in the intersection. So like if you remember from before, it'd only be these covered by this little line, these little lines here. Next, let's look at the difference between A and B, so A minus B here. Here we look at everything that is in A and not in B. So we have A, B, C. Finally, let's look at the difference between B and A. And here, all that's included in that one is F, because F is the only element that is in B but not in A. So hopefully this example helps clear up a little bit more about what these different operations do. Okay, so with this combining set section done, let's look at the concept of, let's put it right here. Now let's go up here. Let's look at the concept of subsets, or of complements, sorry. So what a complement is, before we can understand the concept of a complement, we have to understand the concept of a universal set. And a universal set, let's just start with an example here. Say we have the set of prime numbers. And for those of you who don't know what prime numbers are, it's just all numbers whose only factors are itself and 1. So an examples of these would be 2, 3, 5, 7, 11, 13. Note that the prime numbers are a subset of the natural numbers. And this is kind of an unstated assumption. When we talk about prime numbers. Oh, wait. Let me actually write an N there. Unstated assumption. Okay, so as a result of this, when we're thinking of things that aren't in P, typically we think of things like numbers like 1. 1's not a prime number. 4, 6, 8, 9. Like all of those numbers we think of as things that are not in P, that aren't prime numbers. However, even though things like, for example, this beautiful new water bottle that I got for Christmas, this is not a prime number, we typically don't think of it as a non-prime number. Even though it's technically not a prime number, it's not in the set of prime numbers. But when we think of things that aren't in the set of prime numbers, we tend to think of them as things that are also considered numbers, that are also in this set, this set of natural numbers. So all this aside, the point of this is to say that almost all sets of numbers that we can think of, or all sets of things, there's this similar sort of unstated assumption that they all belong to this larger set of things. And this set, in this context, N would be the universal set that we're talking about. This is what we mean by a universal set. This universal set is this larger framework in which the particular set that we're working with is located in. So A is the universal set. And almost any useful set that we think about in math can be regarded as having some universal set that applies to it naturally in the context of the problem, and pretty intuitively in the context of the problem. There might be some exception to this, but generally when we think of a set of things, there's a universal set that we think of that can generally apply to it. So with this concept of universal sets aside, kind of defined by example here, the definition of a complement, so let's think about what a complement is. The definition of a complement, so to define this, we're going to think of this set A. Let A be a set, and let A be a set, and we're going to have its universal set be U. And this universal set will be defined typically in the context of the problem. So we'll have a universal set U. So here we'll think of A as like prime numbers, U is this set of natural numbers. So in this context, we define the complement of A, which we'll denote as A prime, or A hat, or AC. So this is the complement. That's the complement of A. We're going to denote it as the set that is, the complement of A is equal to the difference of U and A. So what does this mean in terms of like Venn diagrams? So thinking of a Venn diagram here might be a little bit more or less intuitive, but because it's not a Venn diagram where of two circles, because given that it is a set with universal set U, we know that A is a subset of U. So we can think of this U as like this broader framework. U is the universal set. Everything in here is that universal set. And then A can be this circle here. So this circle is all the elements of A. U, everything inside of U is the universal set, and A is a subset of the universal set, so A is entirely included within U. So the complement of A, on the other hand, is everything shaded here. It's everything that's in U but is not in A. So that would be the complement. So for an example, let's go back to our prime numbers example. In our prime numbers example from above, let's scroll up here. So let me zoom out a little bit actually. In our prime numbers example, I'm gonna like cut this off actually. Yeah, well, remember the prime numbers from before. That it's, oh wait, sorry. I need to include a dot 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 here. Sorry, oh my gosh. Yeah, so I didn't include the dot 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 here, but it goes on forever with all the prime numbers. That was a mistake. Okay. So this example, so we have P is a subset of the naturals. So P is the subset, or is the set we're curious about, and the naturals are the universal set. So in this context, the complement of P is all of the numbers that are contained by the natural numbers that are not contained by P, that are not prime numbers. So in this context, the complement of P would refer to 1 and all of the composite numbers. 1, 4, 6, 8, 9, 10, dot, dot, dot. This time I'll include the dot, dot, dot. Sorry, when recording this video, sometimes you just make like little... I never understood how my professors did it in the past. I was like, oh, how are you making such an obvious little mistake? But now, like, actually writing this out and trying to like present and record it, it's like, oh yeah, you do make like these very, very minor mistakes. But okay, so basically the complement of, or like you make these very, very obvious mistakes sometimes. But here, okay, so the complement of P is 1, because 1's not a prime number, and the set of all composite numbers. And this would be the complement of P. It's all the numbers that are not prime numbers, that are not in P, that are also contained by the set of all naturals. Okay, so with all of this in mind, this is a brief introduction to all of the notation and what a set is, and all the notation that will be used in set theory. And since sets are kind of a basis for proof, these sort of concepts appear all the time throughout proof. Sets are kind of the basis for modern mathematics. Set theory is incredibly important, and people try to use set theory as kind of this theory, underlying theory of math, this underlying theory of everything in math. But one thing that's important to keep in mind is that the way we define sets is very important. So up here, I gave this definition of sets that is very, very, very simple. It's just a collection of things. And for in early math history, this definition worked fine. Or in earlier math history, for most sets, this definition works fine. But there is a need for some restriction on this. We can't just define some rule and say the set is everything that aligns with this rule. And to see the reason why we have to go to Bertrand Russell. And Bertrand Russell is a British mathematician and philosopher, and he did some groundbreaking work on on set theory and some of the foundations of mathematics. So he's incredibly important in the field of math. And what he discovered was a very famous paradox called Russell's paradox that kind of exposed how a misuse or an unrestricted use of sets can lead to these sort of bizarre and paradoxical situations. So to understand what Russell's paradox is, let us start by defining the set that makes all of this possible. Let me actually change the heading here too. So we're going to be talking about Russell's paradox. So starting here, let's first define the following set that makes all of this possible. So A is the set of sets, or set of X, where X is a set. So set of sets that where X is not an element of itself. So what does this mean? This is the more technical definition of it, using the notation that the set builder notation we talked about before. But in more layman's terms, A is defined as the set of all sets that do not include itself. The set of all sets that does not include itself as an element. So what does this mean? This is a bit of a weird sounding, circular sounding definition of a set. But what this means basically, let's think of some examples. So let's start with something that isn't an example of this, or that is an example of something in A. So the set of all integers is in A because the set of all integers is not an element of itself. Note it's a subset of itself, but it is not an element of itself. The set of all integers is not an integer, in the sense like the integers are -1, -2, 3, 7, 200, but the set of all integers is not one of those elements. So because of that, the set of all integers is not a set that contains itself, so it belongs to A. Additionally, the empty set belongs to A, since the empty set is not an element of the empty set. The empty set is just this set. It does not, the empty set is not inside these brackets. Note, the empty set is contained by this set, or is an element of this set, but the empty set is not an element of this set. As a result, the empty set is in A. It is a set that does not contain itself. However, let's think of an example of a set that does contain itself. Let's define the set as, simply we can define it as this. But expanding this out, we get this. It's kind of the set that infinitely closes on itself, or that holds an infinite number of elements. It's a set that kind of recursively contains itself over and over and over and over and over and over and over again. Note that B is an element of B. So B is not an element of A because it contains itself. So it is not a set that does not contain itself. Okay, so with all of this out of the way, I hope you kind of understand how this set works. It's the set of all sets that don't contain themselves, basically. So I hope you can kind of understand how this set works. If you want, try to think of more examples of this sort of thing. Most sets that you can think of, and most sets in math, would belong to this set of all sets that don't contain themselves. Now, the paradox here arises when we ask this question. Is A an element of A? Does this set that we defined before, the set of all sets that don't contain themselves, is that a set itself? Or does that contain itself? Does the set of all sets that don't contain themselves contain itself? It sounds like a word salad, but it's actually very important here, because what happens here is, if we define this set like this, if A is a set that contains all sets that don't contain themselves, well, is A part of A? Well, let's first look at if A is an element of A. Well, if A is in A, if A is one of these sets, then A is a set that does not contain itself. So that means that if A contains itself, then it doesn't contain itself. Let's write this out differently, actually. Okay, that's fine. That means that it's impossible for A to contain itself, because that leads to a contradiction, right? Well, then let's look at this next case. So that means A doesn't contain itself. By the law of excluded middle, if this is a contradictory statement, if this leads to this contradiction, that A contains and doesn't contain itself, then that just means that the other case must be true by law of excluded middle, right? Well, if A does not contain itself, then it is a set that does not contain itself. And as a result, it is included in A. Once again, we have a contradiction. Both cases here lead to a contradiction. So as a result, we have a paradox. What it leads to, ultimately, is this sort of infinite chain of, oh, so if A contains itself, that means A doesn't contain itself. Well, since if A doesn't contain itself, that means A is an element of A. Oh, wait, sorry. That was a mistake. That means that A is an element of A. Well, if A is an element of A, then that means that A is not an element of A. And if A is not an element of A, that means that A is an element of A. So, and this keeps going. Like, this is just a paradox. And as a result of this paradox, we realize that we have to move beyond this naive approach to defining what sets are. We need to start having restrictions on how we can define sets. We can't approach math with this naive set theory that doesn't restrict how we can construct sets. And instead, we need to develop an axiomatic foundation to set theory, to say what sort of things are allowed to be sets, what sort of things are not allowed to be sets. And based on all of this, we came up with the Zermelo-Fraenkel Axioms to resolve this. And I actually haven't heard this word much. It's more one of those words that I've read more than actually heard someone say. So if I'm pronouncing this wrong, feel free to correct me. It's one of those situations. And these axioms basically define what's allowed to be a set, what's not allowed to be a set, and they serve as this foundational starting point that we can construct set theory based off of in the future. And ultimately, they prevent Russell's paradox from arising because they rule out the possibility of these sort of circular sets based on the Zermelo-Fraenkel axiom, or the Zermelo-Fraenkel axioms. We can't. This set doesn't make sense. We're not even able to define this as a set. So basically, as a result, the Zermelo-Fraenkel axioms resolve this problem, and they serve as this axiomatic foundational starting point for set theory, and then ultimately for mathematics, if you believe set theory is kind of the foundation of mathematics. Now, further discussion of these axioms is beyond the scope of this video. This is an introductory video. I was trying to look into like if there's some way to explain how these axioms work in a very like simple layman sort of way, but it seemed like most explanations like you can get there, but it just would take a whole other video in and of itself. So discussion of these axioms I'm going to leave beyond the context of the scope of this video. This is an introductory video, but ultimately what we found is that these axioms resolve this paradox, so now we can move forward with set theory, basically. And with all of that in mind, I hope you all enjoyed. That's all I wanted to go over today. And so for next month, I'm planning on releasing an introduction to mathematical proof, where we take all these concepts, where we take mathematical logic, where we take set theory, and then we start going into proofs of things. So with all of that, that's all I wanted to cover today. And if you enjoy this content, please like and subscribe, and feel free to leave a comment if you have any questions or believe I made a mistake somewhere in this video. Yeah, so I'm sure there's points obviously where I've made little typos or miswrote something, and I'm sure there's some instances where I've said something slightly off, so feel free to correct me in the comments, and I'll try to clarify what I meant by different things down there. Or I think that's all I have to say for this video, so please like and subscribe, and without further ado, thank you all for watching, and I hope to see you all in the next video. Peace.